In the last video, we explored how to calculate confidence interval using sample means to estimate population parameters like systolic and diastolic blood pressure. But the true power of confidence intervals lies in comparing these variables across different exposure levels. So in the next few slides, we'll talk about these concepts. Thank you for joining. We might be interested in knowing if there is a statistically significant difference in the mean age at which chronic heart disease is diagnosed between males and females. In this case, our exposure is categorical, which is sex, male or female. In most of the cases, we do deal with exposures which are in categories. For example, BP, maybe cholesterol status or weight status or any other categories. But here, because our outcome of interest is continuous, so our results will be a continuous variables, which is like the mean age at which chronic heart disease diagnosed for males versus for those for the females. So in this case, our objective is to calculate and interpret the 95% confidence interval for the difference in mean age at chronic heart disease diagnosis between males and females. And if the 95% confidence interval does not include zero, the difference between males and females is statistically significant. But if it does include zero, we will conclude that there is no significant difference. We have now seen this slide a few times now. In first step, calculating the standard error and then calculating the upper and lower bound of confidence interval. Take a closer look at the formula itself and then we will move on. When we are calculating the confidence interval for the differences in exposure levels when dealing with continuous outcomes, the steps are almost exactly the same. The only difference is that the formula to calculate standard errors is now slightly different, because now we have to factor in the standard deviation of if there are two populations, then we have to factor in the standard deviation of both the population. For example, we might be comparing the systolic blood pressure difference between males and females, and in that case we have to calculate the standard error based on the standard deviation of males divided by the number of males in that sample, and the standard deviation of females divided by the number of females in that sample. And then once we have calculated the standard errors, rest is the business as usual. We will be adding two standard errors to the sample mean to get the lower, we will be subtracting two standard errors from the sample mean to get the lower confidence interval, and we will be adding two standard errors to the sample mean to get the upper confidence interval. We are not going to do it by hand. Nowadays, it is very easily being handled by the computers. But the basic point is that we need to understand that how standard errors is calculated and how specifically the standard deviation or the deviation within the sample and the sample size plays a role in calculating the standard errors. And all you have to remember is that as there is more deviation within the sample, your standard error is likely to be larger, and then your confidence interval in turn is going to be wider. And conversely, if your sample size is larger, your standard error is going to be much smaller. Let me turn on my flash. So the standard error is going to be smaller, and in turn your confidence bound will be more precise and more narrow. Let's do it on SAS, and we will talk more about that over there. Go to Task and Utilities. On the task under Statistics, let's run t-test one more time. Okay, you can use fhs_lib.heart2 or Let's use Heart-1 for now. We'll use Heart-2 for some others, for other demonstration. 2 sample t-test, and let's use age at which chronic heart disease was diagnosed as our analysis variable, and grouping variable be sex. Okay, and in the options tab, I'm going to keep all the default options, except I'm going to change it to plots. I'm going to keep all the default options now. Okay, let's run the test and see the results. Okay, so here are our results. This is table number 4 from the top, probably. We see that the women on the average are diagnosed with chronic heart disease at the age of 65.6, while males are developing chronic heart disease at much earlier age, almost 4 years earlier, that is at the age of 61.6 years. And that is the difference of 4 years. So the males are developing chronic heart disease 4 years earlier than females, right? And at the same time, we also see the 95% confidence interval given right next. For the population, we are 95% confident that if we repeat this test multiple times, our difference will stay between 3 to 5 years for the whole population. And since this range does not contain 0, we conclude that there is a statistically significant difference in male and female in their age at which they are developing coronary heart disease. In some cases, it might make more sense to have your outcome in categorical variable. For example, we might have a research question which asks, is there a statistically significant difference in the risk of high blood pressure between male and female? In this case, the risk of high blood pressure is a categorical variable because it will be the proportion of high blood pressure. And then we will be comparing the proportions instead of the actual continuous systolic blood pressure. So in this case, our exposure remains the same, the male and female, which is a categorical variable. Now our outcome is also categorical because it's the proportion of individuals with high blood pressure. So the objective of this research would be to calculate and interpret 95% confidence interval for the relative risk of high blood pressure between males and females. And if the 95% does not include 1, please note that now we are not looking at 0. Anyway, I will explain why it is 1 and not 0. So if the 95% confidence interval does not include 1, the difference between male and female is statistically significant. But if 95% confidence interval does include 1, we conclude that there is no statistically significant difference. Because just think about it. If 20% of the males have high blood pressure and 20% of the female have high blood pressure, so when we are comparing these proportions, 20 over 20 would be 1, which means that there is practically no difference between males and females. We will be talking in length in chapter 6 when it comes to categorical data analysis, but in summary or in short, we will just learn that when it comes to measuring the confidence interval for differences in exposure, when there is a categorical outcome is involved, the only difference in the calculation would be the formula to calculate standard errors, which appears a little bit complicated, but the concept remains the same. it is the proportion among the proportion of the the risk, which is high blood pressure, divided by in males, for example, divided by the number of males in that sample, and then the proportion of females who had high blood pressure divided by the total number of females in that sample. And this would be underscored. Once we have calculated the standard error, then rest of it is going to be the business as usual. We will be just adding and subtracting two standard errors from the proportion to get the confidence interval. Okay, in our original heart dataset, or heart, sorry, this one, we have BP status, but it has three categories, as we have seen it many times: normal, high, and optimal. I will convert them into two categories, and because that will be easier for us to understand how the confidence intervals for the proportions work. So let me, in fact, we did created a BP status 2 in chapter 1, but for some reason I got it deleted, so I'm going to create this variable again. Okay, so I will go to task and utilities, because now we are dealing with the data set itself. So I will go to data tab and recode values, BP FHS underscore lib dot heart2 variable to code is BP, sorry, this is a character variable, which is BP status, and the new variable, I'm gonna call it BP underscore status 2, and I'm gonna write to input dataset in the same dataset. I'm going to have the old value high as still high, and then I will have normal as normal, and optimal is also normal. So I'm converting three categories into two categories now. I'm going to submit the code. Okay, now I'm going to go back to heart2 dataset over here, and I see that a new variable BP status 2 is now created, which has only two categories, and I'm going to put them side by side, BP status and BP status 2. We see that all those who had optimal blood pressure are also now labeled normal. Okay, so now go to task and utilities. Under task, under statistics, double click on table analysis. Okay, and row variable is going to be our exposure, which is in this case is sex, and our column variable would be a BP status 2, which has now only two categories. And then on the options tab, I'm going to keep all the default options. The only thing which I'm going to add is odds and relative risk, and that's it. I'm going to submit the code. Okay, so here are our results, and if you look at the last table at the bottom, we see that the odds ratio, that is 81:62, which means that the females have almost 11% lower chance. That means that the females have 81% of a chance of developing high blood pressure compared to males, which means that they have 11% lower odds of developing high blood pressure. And it is also giving us the confidence interval, which is 73% to 91%. So since this confidence limit doesn't include 1, So we see that this difference is statistically significant. It has also given us the relative risk, which is again almost, I would say, no, over here it's 19% difference. I'm sorry about that. There's 19% lower chance of developing high blood pressure for the females compared to males, and the confidence limit is 73% to 91%, which means that they have, even on the other end, close to the neutral value, they still have 8% lower odds of developing high blood pressure, and on the higher end they have approximately 27% lower chance of odds of developing high blood pressure. And when we are running relative risk, which we will cover in chapter 6, in fact, we see that they have the females have 11% lower risk of developing high blood pressure, and the range is between almost 6% or 5% lower relative risk of developing high blood pressure for females compared to males. To the other end, it is almost, I would say, 16% lower relative risk of developing high blood pressure. See you in the next video.